The broadcast is now starting. All attendees are in listen-only mode.
Hello, everybody. Welcome to this month's webinar for SLCan. It's Kevin Humanick here from the Professional Development Committee. Thank you for attending. Today's presentation will be made by Matthew Crouch from CamFil. His topic is Understanding HEPA Filter Media and its Impact on Biosafety Environments. I'd like to introduce Matthew. Many of you know Matthew from the conferences that we've held in the past, and he's also presented webinars for us, so we appreciate him having him back. Matthew oversees CamFil's sales and marketing efforts directly related to the pharmaceutical, biotech, and laboratory space for North and South America. Matt has spent his career involved in the life sciences market, starting in academic research before moving into two biotech companies and a well-known pharmaceutical firm. With 10 years of experience specializing in the air filtration needs of high purity and critical environments, Matt has been of service to labs all over, from the north, the frigid north, to the barren desert, deep into the rainforest, and even 2,000 meters underground. So thanks, Matthew, for joining us today. And without further ado, I'll pass the mic.
Thanks, Kevin. Appreciate that. So hi, everybody. Thanks for joining us today. Let's jump right into it and why we're here. So we're going to talk a little bit about the why HEPA filters. And again, some of you who attended my webinar last year will have seen some of my slides, heard some of this before, but we're going to go back and discuss a little bit about why we have HEPA filters, what they do, and why they do it, because it's obviously critical to the biocontainment and life science space. We'll talk a little bit about standards and testing, and then we'll touch back on that again in the conclusion through media types and different choices. So there's choice, which is fantastic. Many of you may not be aware that there are other choices other than microglass, which is kind of the market standard. It's been around for well over 50 years. There are new options as far as medias are concerned, and we'll discuss some advantages and disadvantages, where to use them and where perhaps to take a little bit of caution. And then obviously we have an open forum for questions at the very end. So Kevin gave me a nice little lead-in intro there, but just a little bit of my history and past. I've been doing this for a while from the filtration side of things, and I'll put up my contact info at the end so you guys can reach me if there's any questions or concerns at the end of the presentation. If you want to chat a little bit more. Not an issue, or you want to ask me when I was 2,000 meters underground, that's an interesting story. I'm happy to talk about that one. So as far as the take-home message, filters, not just filters, not just filter. And of course, the filter is only as good as the housing it sits in, and a housing is not just a housing, it's not just a housing. So jumping right into HEPA filter media, the first thing I'm going to state is something that we do as children, but we fail to do really well as adults, and that's ask why. So why do we use HEPA filters? Why are they the way that they are? What shaped that? What forces of nature gave us the glass HEPA filter in its current form? So one thing that I will provide as well with the slides for the group is a list of references. So this reference list is always being updated and changed. This is to show that what we're talking about here is academic research, studies, references for real life data. It's not marketing materials, it's not promotional materials that were developed by a bunch of MBAs sitting in a room cooking up what they think would be really attractive. It's actually market studies and university studies. And that's really important as we get into some of the science that we're going to discuss. Don't worry, we're not going to go into too much physics, but we are going to graze over some of it. And obviously, as we're talking about different medias, it becomes more and more critical that we have fundamental questions answered instead of just a bunch of people making stuff up. So we'll go back to basics. Why do we have filtration in general? Okay, really quick. We bring air from outside into the building. Now again, we don't classify that as fresh air anymore. Now we classify it as outdoor air. Why? Because we know outdoor air is no longer fresh. It is contaminated. So it does need to be cleaned when it gets into the actual space where we have individuals working or perhaps producing research materials or pharmaceuticals, for example, or some kind of products. So we take it through the air handling unit. Air handling units are fantastic at heating, cooling, humidifying, and dehumidifying. They suck at air filtration. So we need to make sure that we have good filters in place to be able to remove the particulate, which then gets sent into the workspace or again into the lab space. So then we have two choices. Now that the people in the room or the process in the room has contaminated, sorry, I'm north of the border, process. I can say it properly now. When you're inside the space and you contaminate the room, we have two choices. We can either take the air and dump it back outside, which could be a costly measure, especially if you have to heat, cool, humidify, and dehumidify it again, or we can recirculate it within the space, but we need to make sure that we're removing the contamination particles from that air. So what kind of particle size are we talking about? And again, we're just going to glaze over this. We're not going to dive into it too far, but really what we're interested in is what we call PM10 and smaller. That's particulate matter 10 micron and smaller. We're not interested in larger than that, especially when we're dealing with HEPA filtration, because we want the HEPA filter really concentrating on these small particles that general filtration either struggles with or cannot do. So when we're talking about microbial size particles, as you can see, PM 2.5, particulate matter 2.5 micron or smaller, that's where you're going to hit 90% of your bacteria. As you get even smaller than that into PM1 category, you're going to see your viral vectors or your viruses. Now, this is really where we want to pay attention from a biosafety lab standpoint, because obviously if we're working with an experimental vector, it gets out into the public, we have a massive issue. On the nuclear side of the map, which I also look after, nuclear is fairly straightforward in the fact that if a stray particle gets out, it's usually thousands of meters away from public exposure. And at the same time, once a nuclear particle is introduced, it immediately starts to degrade and lose its efficiency. Bacterial and viral vectors are different because if they find a host, they immediately start to replicate. So we're looking at a totally different game plan. Even one gets out, that can be catastrophic in comparison to a radioactive material where a particle gets out. Okay, you get a text alert on your phone apparently, but it doesn't necessarily mean that there's a real cataclysmic event that's going on. So air filtration standards, and again, we're not talking about the so-called MERV 1 to 16 filters and their efficiencies. We're really talking about HEPA filters. We're talking about a much different monster. So we're not going to talk about that in this presentation. Really what contamination is by definition, okay, is an outside vector or an outside material that contaminates or gets within a space where there are active participants or an active production. Okay, and how airborne contamination can enter is very straightforward. I mean, it can go through supply air, it can be shed directly from room occupants through coughs, personal hygiene, etc. It can be a result of the process itself, transferred from adjacent rooms or spaces, which is not only doors being wedged open, but also natural leaks or holes or cavities within the lab space, which in a biocontainment lab should not be present, but in a hospital or something along those lines, they definitely are. And then in the case of, in particular, an operating room, in this case, you're looking at cracks in the ceiling or cracks in the trim, holes in the housing, etc. So what is an actual HEPA filter? Let's go through some of the physical properties of a filter. The media that you see on the left is microglass. So that's a blown up cross section of what microglass looks like when it's really close up. The origin of the HEPA filter is fairly interesting. It was actually originally cited for nuclear work when they were designing the atomic bomb. And the US Army originally dubbed it as an absolute filter because it had to stop absolutely everything from getting out of the lab in the research space. So that name carries through today. There's one particular manufacturer that shall remain nameless that still calls their filter an absolute filter because of that association with the original onset of the creation of this filter. So it exhibits four basic properties, okay, straining, inertia, interception, and diffusion. Straining is fairly straightforward, where the particle is lodged between the actual fibers of the media. Inertia, again, fairly straightforward. The particle directly contacts the media. Interception is a little bit different. It's more of a basic polarization or van der Waals association, where a tiny particle is attracted to the media, which is far larger. So it kind of acts as if it has a gravitational pull, which pulls the particle in. And then diffusion, which is basically the smaller the particle, the more chaotic its random molecular motion. So as that particle becomes smaller, it moves in such a chaotic path that it actually runs into the media by accident. And you can see this in practice by modulating the airflow of your filter and how it loses or gains efficiency by going over or below the rated flow rate. So there's many different types of HEPA filters. We're going to concentrate this discussion on two, primarily on the panel, so-called panel type, which is primarily for clean rooms or operating or hospital theaters. and then the box style, which is more traditional biocontainment type product. Now, if you are familiar with some of the newer BSL-3 labs or BSL-3 plus labs that have gone into Canada in the last several years, you'll be very familiar with the panel style HEPAs. It's because we are starting to use those more frequently because they're more cost effective. And again, if you're using more housings and you're using more air distribution within the space, then you don't have to worry so much about having the big hunky box style. You can use the panel filters and do just as good a job of containing your particles. So you may not be familiar with that. The panel style comes more from the pharmaceutical microelectronics industry. The box style HEPAs, which is more traditional bag and bag out containment, they've been around for a very long time. Their design really hasn't changed too much. Conventional gel seal when it comes to North America, though you do still see some archival gasket depending on the firm and when the original product was designed. So what do HEPA filters actually do? Well, they capture everything. This slide is from last year for those of you who were nice enough to join us back in January, where we did a quick Q&A on HEPA filters. Once again, just as a quick review, HEPA filters are really good at filtering gigantic particles, but that's not why we spend the money. We don't want them installed to do anything over 10 micron. We want them smaller than that, so PM10 and below. That's really where they shine. So what you'll also see is this curve falls off at a size we call MPPS, or most penetrating particle size. That's down there at the 99.99% efficiency. That's this strange curve where we see more particles bypass the media in comparison to other sizes. So we also test and challenge HEPA filters to that size because it's more frequent to have a particle bypass it. That's the particle size that we're most preoccupied with when it comes to the filter. What you'll also see is that the efficiency starts to climb again after we pass that MPPS rating, and it begins to skyrocket as the asymptote approaches back to 100%. And the reason for that is the diffusion principle that I mentioned a couple slides ago, where the particles become smaller, there's random molecular motion, and as a result of that, it runs into the media, which increases the efficiency of the filter again. So when do I change my HEPA filters? How long does a HEPA filter last? How long is a road? So previously, we were only able to test HEPA filters to validate whether they were still in practice or still in efficiency. I'm going to show you some new technology that has actually changed that, working towards an actual time limit as to how long you can have a filter in play, which is a bit of a shift in the industry. And there's obviously some questions that come along with that as to how the industry is going to react to that change in technology that we're seeing globally. So do filters have to be tested after installation? Yes, they do. And why is that? Because obviously during installation, you have very fragile material such as microglass. You could have damage to the media. The other issue that we run into is the actual frames matching up with the HEPA filters. So there is bypass, there can be bypass, there can be compromises in the material of the HEPA. So as a result of that, we test once filters get into play, just to make sure that the media efficiency is maintained after it's been installed. So who sets the guidelines? That depends on where you are in the world. Typically in North America, we would utilize IEST, though we do use EN 1822 or the Central European Standards option as well, again, depending on what's the application and depending on who is setting the standards. So it does vary depending on the firm. However, obviously you would set it to a certain guideline and then you would test accordingly. So that's kind of our quick review. Now we're going to get into a little bit more depth as far as what is a HEPA filter, what's the media composition, and what's the difference between them. So let's start at the beginning. Microglass. So that's something that's been around for a very long time. Hopefully everybody on the call has seen a HEPA filter, touched a HEPA filter, maybe even had the opportunity to install one or certify one. So you're very familiar with the monstrosity we're going to talk about. So the concept behind glass or microglass filtration is really depth filtration. And the media itself was found, again, as I said, from the Manhattan Project and originally from the nuclear industry. But microglass or glass fiber really came by accident. They were really trying to find something that was able to stop these really small particles. It was not engineered to be a HEPA filter. It was just, hey, this media works the best. Well, we have a timeline because we got a war, so let's move that up. We'll just use the media and go from there. So as far as that's concerned, it replaced asbestos, as we know, which is a known carcinogen. Okay, asbestos didn't even do as good a job as microglass. So obviously microglass replaced it, implemented it within the technology, and commercialized to the public in the 1960s. So it's been around for a long time, and it's kind of the, yeah, we've got it, but there's really been no reason to replace it. The technology that's been introduced really doesn't compete with what it's capable of doing, so we've kind of made do with what we have. So what does it look like when it's blown up? That gives you a cross section of the media on the left, and then a digital rendering on the right. And I apologize, it's kind of a close encounter of the blurred kind. But if you see in there, you can really pick out solid particulate, which is lodged in between the glass fibers, which attract those the larger particles, and the smaller particles and lodge them within that depth. So if you wanted an analogy for microglass, I usually use the jungle analogy. So if you're running through a jungle at full speed, you're going to run into something, because jungles are very dense, very thick, and there's lots of different depths. So even if you pass the first couple trees, odds are a stump or another bush is going to hit you. So one way or another, particulate's going to be stopped within that mess. One of the other medias that was introduced over 20 years ago is actually what's called expanded polytetrafluoroethylene, or PTFE. And some people have misnamed this as Teflon, which is not technically correct. It's not Teflon. Teflon is actually just PTFE. This is expanded PTFE. Teflon is actually what you see in window wipers or in pans that's being sold on the shopping network or at Canadian Tire. It's not what's used in filtration. So the first ePTFE filters were produced in the 1990s, so a little ways ago. I'm not going to tell you what I was doing in the 90s. Don't worry about it. And they were very high efficiency for microelectronics, so U16, U17 rating, which is the so-called ALPA filters. Beyond the scope of this discussion, but again, it was designed for incredibly high filtration efficiency. And it was very well received by the microelectronics industry because of the efficiency of the media. It actually allows for a lower pressure drop than glass. So as a result of that, it's very cost effective for operations that are running very high airflows. The problem with it, however, is that if you ever have to buy one, they're incredibly expensive because it's a very particular manufacturing process. It's not typically used. And so as a result, they were very expensive. So they were not commercialized in the 90s because there really wasn't the ability to commercialize them at that time. Since then, a well-known air filtration supplier has purchased or was purchased by a company who purchased the rights to ePTFE. And so they've been pushing it a lot, especially in the life science or bio space. The challenge when it comes to PTFE is its efficiency as a result of its construction. So in the way that glass filters through depth filtration, PTFE does not have the ability to do that. It is a razor thin membrane. So as you can see in my diagram here, you've got two very large backing layers, and then you've got an actual filtration membrane layer. And what that looks like, the digital renderings on your right, and then the actual cross-section and electroscanning microscope is on your left. So you can see that put into practice. So the backing layer provides no filtration whatsoever. It's really just there to create a rigid surface. So as a result of that, PTFE is fairly durable. It's allowed to forgive handling as a result. However, its efficiency falls quite low because the membrane loads very quickly. So even if it does have a very low pressure drop to begin with, it quickly builds and soon is out of service. So again, for a fairly expensive filter, it's compromised very quickly. So what's usually done in the industry to offset this is to create multiple layers. And the analogy in this case is actually a row of trees in a forest. So take away the jungle backing and just put a bunch of trees together. So on its own, yeah, if you're running through that forest and you kind of don't pay attention or you're on your cell phone, you may run into a tree and you may stop. But for the most part, you're going to be able to bypass that layer. So they have to keep putting more and more layers into the actual membrane to be able to stop particles. So if you miss one tree layer, maybe you'll hit the second, maybe you'll hit the third, maybe you'll hit the fourth. Each subsequent layer, however, creates pressure drop. So you're actually compromising the design and the efficiency of the pressure drop decrease by adding more layers to compromise back and fix the air filtration side of things or the removal of particles. So really that takes us to our current situation. So we've got 70-year-old technology and 30-year-old technology and kind of how that all sits together in the industry. Glass fiber, again, has a fantastic lifespan. So if you've been around, you know that a glass filter left in service with absolutely nothing touching it, no testing, no handling, it can last for a good solid 10, 15, 20 years in operation without compromise. However, the reality of that is things tend to happen, whether that's a sprinkler going off, whether that's a technician dropping a wrench, whether that's just general particle wear and tear through the years, the media eventually becomes compromised. So there is a fragile nature involved in that. Membrane technology, as I said, there's the example being ePTFE is one example, nitrocellulose membranes being another one. As far as the plus sides are concerned, very energy efficient, very, well, I should say better than glass, not necessarily very. And again, no boron. So we'll talk a little bit about that in the microelectronic space, but in the life science or biospace, there's really no issue when it comes to boron contamination. In microelectronics, it compromises the process for manufacturing. But the downside, again, is lifetime, because again, we're looking at a media that either allows a lot of particles to pass through, or we have to layer upon layer upon layer, which creates an artificial pressure drop. And of course, it loads very quickly, compromising the filter in general. So what does that introduce? That introduces a nasty word that we hate called risk. So especially if you're like me and you come from the pharma industry, we hate the word risk. When you're talking to Health Canada and you're talking about risk, obviously that's a major issue for us on the bio side as well. We don't want to introduce risk. And right now, the best solutions that we have in the industry inadvertently introduce risk, okay? Because there's a chance of failure in the filters, there's a chance of failure in the media. So overall, we're dissatisfied, right? Is there any way that we're in this fantastic age of AI and computer-generated models and manufacturing and 3D printing? Isn't there a way that you can kind of upgrade the current standards in HEPA filtration and basically be able to take all the best aspects of glass and the membrane medias, okay? So solid particle loading, the durability of PTFE, chemical resistance, service life of glass with the low pressure drop of membranes, and basically take away the easy to damage and the rapid loading or rapid aerosol loading. And essentially that's what we're after. That's the gold standard that kind of the industry has been lacking for many, many years. So recently we've seen a new media come out on the marketplace that was launched last year. Some of you may not be aware of it, but it is a new technology that basically merges the two concepts between glass fiber and PTFE. And it's referred to as EnerGuard media in particular. So really what it is, you'll see that it's analogous to glass as far as the way that it loads. It's a depth loading structure, much the same as what you saw with glass fiber, but it does have a similar rigid nature to that of PTFE. So I should mention it is not a PTFE media. It is a different, it's a polymetric media, but it's not the same as PTFE. It's a very different construct. And as a result of that, it's allowed to do the same things that glass can do. So there's your jungle analogy again, depth loading analogy, without introducing the pressure drop that's associated with glass. As I mentioned, it is strong as well. So as an added bonus, it does have PTFE's resistance to touching or handling forgiveness, as it's been referred to in the industry. So these are glove tests or hand tests that were done in installed filters where you can see direct exposure where the thumbs, either an open palm or in that case, a gloved hand has actually compressed the media and there's no residual damage or failure. So from a certification standpoint, this makes it a lot easier for technicians to get into really tight, congested space and be able to change out a HEPA filter without damaging the media for the first time ever. So one of the interesting things that's been done in a couple of different studies, and I'll just mention the one here, which is actually a comparison between the PTFE media and the EnerGuard media. And what you see with PTFE, as I said, I'm not naming names or mentioning any of the companies that manufacture this media. However, PTFE has been actively promoted by one in particular over the last 5-6 years with a number of different compromises in quality. One of the issues that we've seen is very quick loading. So the ePTFE is available with a media that's both resistant to oil and not resistant. So for microelectronics applications where there's no PAO testing, polyalpha olefin challenge, which there typically is in biocontainment and in life sciences, these filters you would think would last extremely well. But premature loading is definitely seen. And in this case, in this experiment, this was done in a life science facility where they actually did challenge with PAO. Not a lot. The concentration is actually at the recommended level of 20 microgram per liter, which is actually quite low, on par with what you should be testing at. And again, it did not last a full year in operation. And that's not unusual, we'll say, based on studies that I've seen in other parts of the world. At the same time, they did another test with the EnerGuard media, and in that case, this is again an oil-tolerant version, so basic microelectronics version, and then there's also an oil-tolerant version for life science and bio. And in that case, it was running at 8 months total operation at 8 PAO challenges at the same concentration, but again, did not see any type of breakdown in the material or fast loading the way that was stipulated within EPTFE. So the other study that was done was on VHP, or vaporous hydrogen peroxide exposure. I know a lot of the labs in Canada use VHP as a decontamination agent. As a result of that, there was testing that was done to determine that the media has no breakdown. There is some fake news out there about glass being eaten by VHP, and that's not true. It's only at extreme concentrations that glass breaks down under VHP exposure. In much the same way, PTFE and EnerGuard are also very resistant to VHP concentrations at a very low loss of efficiency. So in this particular case, this was done in comparison of glass and EnerGuard, and how that works together to show that there's very little loss as far as VHP exposure. In fact, it's almost nothing. Again, if we're working with any type of biosafety space, biocontainment space, we definitely want to talk about microbial inertness. Because generally, if we're working with a bacterial vector and we have anything else growing in the air handler or growing in the space, it just makes it that much worse. So what we want to see is that the media is not promoting the growth of any type of microorganism outside, especially, or inside. So in this case, the testing that was done was quite extensive. It's the Institute for Lufthygiene in Berlin. They are the world-renowned body when it comes to antimicrobial testing or microbial testing. And as you can see, there's almost no growth. There's no growth promoted by the media, and there's very little growth when actual substrates were added to the media in order to encourage growth. So over the years, there's been a couple of companies that have introduced antimicrobial layers into their filtration media, which is usually an ionized silver or an ionized copper, to try to encourage the breakdown of cell layers in the bacterium. We've never been able to demonstrate that that's effective, and ASHRAE has a whole case study. If you're bored on a Friday night and you really don't have anything to do, I'd recommend you look it up, because it's a really good study which explains that HEPA filters, even sprayed with these antimicrobial agents, really don't have an effect on the long-term growth of microbials on filtration media. So it's definitely worth investigating. Again, it's a marketing ploy. Are they really necessary? No, you can get by without them. You just have to have a good filter that doesn't allow bypass, and a good sealant system that doesn't allow air to bypass the filter in the housing. So one of the interesting things about this product that I found fascinating anyway was the onset and the design of it. When it comes to most filtration products that are brought out into the market, it's really a design of convenience. And in this case, it was nothing even close to a design of convenience. It was basically an attempt to solve a real issue in the marketplace. And so I'm just going to highlight the team really quick that designed this grid and created an actual test rig to validate different types of HEPA media. So this is the world's first and only HEPA lifetime test that was performed in a facility in New Jersey in the US. And really the goal of this test was to validate several different manufacturers' HEPAs, all with the same conditions, and done through glass, PTFE, and the so-called EnerGuard media, and how they all stack up and how they work together. So I encourage you, if you get the chance, if you're members of ISPE, Facilities of the Future, there's actually a poster presentation that was done on the EnerGuard and the onset of how it was manufactured. Highly recommend that you log in and go take a look at that. If you're not a member, then let me know. I can provide you with a link to another version, which is not copyrighted by ISPE. But for those of you who are aware, International Society of Pharmaceutical Engineers, the Facilities of the Future show a couple weeks ago highlighted this new technology and kind of asking the questions that I'm going to ask in a couple of slides. So that's the team that really designed the lifetime test rig and the grid. That's a picture of the grid in the background there, where these filters were tested and validated. So what media should we use and where? Because again, there's a couple different choices now. Might be confusing for some. Hey, you know what? What are we going to do with when do we use PTFE? When do we use EnerGuard? When do we use glass? And the long and the short of it is, you want to use glass? Really, keep using glass. It's not necessarily a huge reason to change at this time. As the technology evolves, that might change. But right now, if glass is working for you and you're not having breakdowns, you're not having issues with testing, stay on the status quo. There's no reason to investigate that. But after all, this is a forum for sustainable ideas and sustainable technology. So I want to put one thing out to you guys. If glass media breaks down and has issues with handling and the like, then perhaps it's time to start considering a next generation technology in order to be able to increase the sustainability of your facility. And again, if Megalam EnerGuard uses a lot less energy, it might be worth considering how much energy can I save in the facility by switching a HEPA filter that's going to be in operation for 10, 15, 20 years. It could be quite substantial. So air filtration need, what media do you use and where? So if we need to certify the HEPA performance with PAO, I would recommend you go with microglass. Why? Because it has been used with PAO testing for years. There's no clogging, there's no issues. Are you testing with PSL, polystyrene latex spheres? If you are weird and kind of unusual in the market. No offense, but it's not something that we usually see in the biospace. It was designed to test PTFE. So if you are using PSL already, then PTFE is a great choice for you. I would say probably 0% of Canadian biolabs are using PSL, so probably not being used in your facility right now. And you do need a whole other certification technology in order to use them. You can't just switch from PAO to PSL. You have to buy a different particle counter. You have to buy a different nozzle. It's a completely different monster to adopt. So if you're an FDA regulated or Health Canada regulated facility, you probably want to stay on what you're using already, or you want to be ready to explain why you switch to a PTFE media, for example. Change filters on SOP or every 2 to 3 years anyway. Really doesn't matter in that case. You can use either or. Just again, PTFE is going to be a lot more expensive than microglass. So if you're going to change them out, you should probably be cognizant of the cost as a result of that. Is off-gassing a concern? So the reason why I highlight this is because of testing methodologies. So microglass is tested with PAO. We know that. And as a result of that, you know what you're getting when you purchase a unit that's been tested. The problem with PTFE is that in many cases, it's certified with other reagents, not necessarily PAO. So in some cases, triethylene glycol, for example, has been used as a test reagent. It's used in China. It's used in certain Asian countries. It off-gasses crazily when it's exposed to regular air. So by using PTFE, you may be exposing your lab and your people to triethylene glycol, which may not necessarily be an issue unless you're doing any kind of cloning and you're looking at contamination within transfection rates inside a lab, which could be a primary point of the lab's research. So it could definitely compromise what you're doing. Is laminar flow required? So laminar flow is better in glass than it is in PTFE, just because of the membrane layers. As I mentioned before, the more layers you put in there, the more the air currents become disrupted. And so you lose that laminarity, which you could be looking for within a prep space or within a biological safety cabinet space. And our filters frequently damaged during installation. You definitely want to consider using a PTFE or a membrane in order to protect the handling of that filter. Or from what we've seen in the tests as well, you could substitute in the so-called new EnerGuard media for any of these applications in either place. Because again, it does seem to have both the principles of microglass and of PTFE at the same time without any type of fall off. So it could be substituted in relation to that. So really what comes up from all of this is a question as to the future of the industry. And this is something that I'd like you guys to take kind of into consideration, and maybe you've got some input you can share with me after this, after kind of looking at the pros and cons and what's going on in the industry. From a short-term standpoint, I mean, really, we've seen new medias that reduce or eliminate filter change during installation and routine tests. So that's very new. And again, I mean, biological safety tends to be a little behind the curve. We don't tend to be that much of an early adopter, some more so than others, but it tends to be more of a, hey, if it ain't broke, don't fix it. And obviously the point of sustainable labs is to introduce, okay, well, there are different, more sustainable solutions that we can introduce but it may ask you to kind of step out of your comfort zone for a second. So we've seen that some new medias can really lower your pressure drop and maintain its integrity, even if it's installed by a new technician who's never handled a HEPA filter before and is a little rough with it. EnerGuard, for example, can survive that kind of impact. So the question is really on the midterm. So on the short term, we've already seen these medias. We're already seeing this happen in the world. There are some sites in Canada that do have EnerGuard media installed. Not many that have PTFE installed, and definitely a lot that have glass installed. But in the midterm, really, after we know that the media is intact and we know that the media is not breaking down, is there really a reason to worry as much about the media, or is there more of a focus on the actual housings themselves? And a lot of times, housings are done on the inexpensive, they're done under a bid. And again, if you know me and you've been around for long enough, you know that I hate bids because you never get your value in a bid, ever. I have yet to have one person show me how a bid won them a value proposition to the site. There's always a problem when you bid. That's my soapbox, I'm gonna get off it. But at the same time, maybe in the midterm, we're looking more at focusing on that integrity of the seal, integrity of the merger between those two interfaces, or the air handling unit and the filter, more so than worrying about the media itself, now that you have solutions that will allow for that handling of the filter. And I guess the long-term question that I've had a couple of discussions with some certifiers over the last couple of weeks and months, and kind of ask them, hey, based on this new technology, what do you think? I mean, how do you feel about the future? What are your concerns? And obviously, there's a couple of really insightful discussions that we've had around, well, the industry is going to have to evolve, because if we're seeing media that doesn't break, then are we doing certifications too much? Are we doing them too little? Are we testing the right things? And what does that future look like as far as data integrity and as far as maintaining serial numbers on these filters and progressional filters? If they last much longer than 20 years, should we leave them in place for 20 years? Should we cut them off after 15? There's a lot of questions that are coming up based on this new material. And again, I mean, if you've got something to weigh in on that, I'd love to hear from you as to what you guys might think as, okay, well, as these integrity tests change, what should that look like for a biosafety facility or Health Canada? Or as a certifier, hey, do you think certification should remain constant even if we do have media that we know is not breaking down? Should we just be testing anyway because it's better safe than sorry? Or could we be using that time and technology for something else to test another valuable resource within the facility? So what does that look like? And ultimately, who decides? Is that a Health Canada? Is that a regulatory side of things? Or as end users and as facility managers for these labs? What's your input as far as, hey, if the filter media doesn't break down, then I'm just going to keep running it the way I'm running, and I'll have my my technicians do integrity tests every so often just to make sure we're all good and compliant. But at the same time, the media kind of covers all that, and we don't need to worry too much about it. So that's an ongoing discussion that's in the industry right now. There's no right or wrong answers. There's just, hey, what's going on out there, and what do we think is kind of neat in that aspect. So summary and conclusions. So hopefully from this, you can take away that different HEPA media can and should be utilized based on their ideal operating environments. So again, I always recommend that the media match the application. And if you're not sure, ask some questions, because there are professionals out there that can help direct what might be the best solution. But ultimately, a scientific approach is always the best. So don't buy the hype, ignore the fake news. You see marketing brochures, whatever, flashy videos and nice graphics on LinkedIn, that's fine. But definitely do the research, look at the studies, and look at how the media was put together. And credible research is the way to go, because in that way we know that what we're putting in is actually biologically safe and helpful within our facilities. So that's an old slide, but I love it, and it's in almost all my presentations. I hate copy paste. I mean, it's fantastic for Word, but please don't use it in designs. Please don't use it in your facility. Obviously, we need to take a step back and consider, especially with sustainability in mind, are we doing the right thing that we were doing 20 years ago? Probably not. The world's changed quite a bit in 20 years. So maybe we need to step back and really consider, is it right to just keep doing the same thing over and over and over again? And one thing, if you follow a lot of the hipster psychology that's going on right now, you'll see the fixed mindset versus the growth mindset. And that really touches on the same thing. It's just a much nicer, newer, updated slide. Really talking about, hey, we're stuck in a fixed mindset in a lot of facilities. Kind of, can we get out of that into a growth mindset to, hey, you know what? let's try something a little bit different. Let's stretch our legs, use something a little bit on the cutting edge, and see the advantages that we can do. We're lucky in Canada because we're well positioned to be cutting edge in the world. We don't have as many restrictions as some countries. We do have obviously some, but we're also a very rich and very intelligent country. So as a result of that, we can come up with a lot of innovative usages for these technologies that maybe some others are a little bit more restricted in doing. So I challenge you guys, take that growth mindset, see where we can utilize new technology and be able to promote a sustainable message to the globe. And just for me personally, and what I always end off with is a filter is not just a filter, it's not just filter. Housing's not just a housing, it's not just a housing. Obviously, I wouldn't be flown around the world and having all these conversations and getting to talk to you lovely people if a filter was just the same as all the other filters. I wouldn't be around. So in closing, that's me again. There's my LinkedIn. If you want to follow my misadventures traveling around the Americas, North and South America, there's always something wacky going on. My email, phone number, LinkedIn, and Twitter handle if anybody wants to follow me on that front.
Thanks, Matthew. I appreciate it. To everybody who's on the line, we are open to fielding questions. If you'd like to submit them in writing in the questions dialog box, and I'll relay them to Matthew. Here we have a few minutes left before the top of the hour. Matthew, I had a question actually related to EnerGuard and the new filter media. Can it be used in existing housings, or does it require new housings?
That's a good question. So the new medias, be it EnerGuard or PTFE, can be utilized within existing housings. There's no reason to change that. The only thing that you really have to be careful of is to make sure that the filter sizes are compatible. So as long as the sizing is compatible, they're interchangeable between housings. The only other caveat to that, Kevin, is the airflow and pressure drop ratings. So because the EnerGuard runs at a lower pressure drop than glass, you want to make sure that you're balancing the airflow to the space to accommodate for the fact that that's going to be a lower pressure drop. So whether that's a constant fan or hopefully if it's a sustainable facility, wink, wink, it should be VFDs. So they'll automatically scale back in order to accommodate that lower pressure drop. But if it's an older facility that's still running on a constant fan, you're going to have to be cognizant of the airflow.
Fair enough, thanks. Another question is, can you explain to me again, or to the group again, how EnerGuard avoids some of the loading issues that you described with EPTFE? With the new technology, because you were explaining that was an issue with some of the EPTFE filters, and not so much with the new media.
So let me run all the way back here. Now I've probably gone too far, and I probably shouldn't have just clicked this 1,000 times and should have just gone manually. All right, so let's just end the thing here. Hang on. It's going to go all the way back to the beginning now. So yeah, that's a really good question. So it's the nature of the media which allows for the avoiding the loading side of it. So if we go down here to look at the PTFE membrane just as an example, and it'll take a second here to kick back up into. It's going to go reverse again, isn't it? Oh, you're going to do that to me, huh? Going to play me that way? All right, there we go. So when you're looking at the membrane here, what you're really interested in, let's get my mouse here. Okay, are these layers up here? So I don't know if can you see the cursor? You can see the little line I'm drawing?
Yeah, we can see that, yeah.
Perfect. So yeah, these are backing layers. So primarily what these backing layers are doing is adding a rigid nature to the media. It's giving it its strength, okay?
Right.
So when you look at what's actually doing the filtration, it's this teeny tiny little membrane layer right in the middle here.
Right.
Okay? So when you add your aerosol, so let's say your PAO, for example, polyalpha olefin, for example, it actually binds to the PTFE media. So as the aerosol begins to bind to that membrane, as you can see, there's very little surface in order to allow for a lot of that oil to bind. So in a very short amount of time, it begins to clog the media
Right.
because there's very little place for it to go.
Right, and we can kind
Now,
of see that. You can kind of see that in the particulate in the picture.
right, yeah, exactly. And because of that really thin layer, the PTFE loading, and again, I mean, that's why you have an oil-resistant version and a regular version. This is a regular version. In the oil-resistant version, all they've done is created another layer here to try, which is actually glass, oddly enough, microglass, where they've introduced it to try to steal the PTFE, or sorry, to steal the PAO away. So that's all it is a layer of glass that's smudged in just over the PTFE layer to try to take that that aerosol away before it touches the membrane. That's how they did it. When you look at, there we go, we're gonna go through here. I'm not gonna click all the way through it again and go crazy because that didn't work out as well as I would have liked it to. So when we look at the EnerGuard media and the new way that it's been designed, you've got the same backing layer. The difference is that PAO can bind to this surface. So now you have a much larger space in order to allow for this aerosol to challenge the media and get absorbed into the media in comparison to a membrane or a PTFE. And that's the reason why it loads so much slower.
So the capacity is for loading is significantly higher because it's the depth is greater.
Exactly. And to be fair, glass loads PTFE glass loads PAO as well.
Right.
So it will bind to glass as much as it will bind to anything else. It's just because of the depth of glass media, it allows for so much more PAO to bind to it. So in much the same way that the EnerGuard media behaves in a very similar manner, it's allowed to load with PAO, and it can handle that that loading.
Great, thank you for answering that. One question about the newness of the EnerGuard media against more traditional glass media. Has there been, acknowledging that there's a number of different variables at play, including facility variables like how often they switch out media or are mandated to, or how they test and handle their media, but has a general analysis been done to show a life cycle cost differential between something like EnerGuard against microglass?
Yeah, there are studies that have been done. They're primarily in the pharmaceutical space, but there is you can do the calculation as far as the reduced pressure drop in the amount of time that your product is in service currently, and you can do a comparison to, okay, well, glass uses this much energy over this much time. If you were to have the EnerGuard media run at an equivalent at a lower pressure drop, then this much energy savings would be given back to you as a result of that differential.
Okay. Interesting. I think that's all the questions that we have for today, Matthew. So on behalf of SLCan, thank you very much for the presentation. Fantastic. Thank you to all of the attendees for attending today. Matthew, I thank you for your time and for a great presentation.
Thanks for having me, Kevin. Always a pleasure.
All right, folks. Thanks again. And don't forget to tune in next month. We'll see you again. Bye, everybody. Thank you, Matthew.
Thanks, everybody. Cheers.